The shell exploded exactly 15 feet from the aircraft. Not 10 feet, not 20, exactly 15. At 600 miles per hour, that precision shouldn't have been possible. Yet there it was, captured on high-speed cameras, undeniable proof that everything the military experts believed about anti-aircraft warfare was wrong, Lieutenant. Commander William Sterling Parsons stood in the darkened screening room at the Naval Proving Ground in Dahlgren, Virginia, watching the footage for the 18th time. Outside, it was 3 in the morning on June 12, 1942. Inside, the only sound was the mechanical whir of the projector and his own shallow breathing. The other observers had left hours ago, convinced they'd seen enough. But Parsons couldn't leave. He kept watching that single frame of the explosion, that perfect 15-foot proximity, trying to understand how it was possible. Because according to every ballistics expert in the United States military, what he was watching couldn't exist. The shell that had just destroyed a radio-controlled drone aircraft contained a fuse that shouldn't work. The designer had violated fundamental principles of physics. The prototype had been built against direct orders. The entire program had nearly been canceled 17 times in the past 8 months. Yet, here was proof, undeniable and repeating every 4 seconds as the film loop ran through the projector, that someone had figured out how to put a radar system inside an artillery shell. Not just any radar system. A radar that could survive being fired from a 5-inch naval gun at forces exceeding 20,000 times gravity. A radar that could distinguish an aircraft from clouds, rain, and the ground rushing past at terminal velocity. A radar that could trigger detonation at precisely the right distance to shred metal and flesh with shrapnel. A radar built by a man the Navy had tried to fire 3 times. A man who'd dropped out of college. A man who'd taught himself electronics by reading textbooks in the public library. A man who was, at this moment, sleeping on a cot in his laboratory because he refused to go home until the military accepted that his impossible design actually worked. Parsons rewound the film and watched it again. The shell rising into frame, accelerating toward the drone. The sudden bloom of the explosion, perfectly positioned. The drone disintegrating, pieces tumbling through the sky like deadly confetti. In the background, through the film grain, he could just make out the observation platform where the designer had been standing, probably holding his breath, waiting to see if his creation would vindicate him or end his career. The designer's name was Merle Anthony Tuve, though most people called him Tony. 31 years old, absolutely brilliant, completely impossible to work with, and according to 17 separate military review boards, wasting valuable wartime resources on a fantasy weapon that would never work. Parsons had read the review board reports. They were scathing, mechanically impossible, electrically unsound, thermally unstable, a waste of critical resources during wartime. Recommend immediate program cancellation and reassignment of all personnel to productive research. The reports weren't wrong exactly. What Tuve was attempting was mechanically impossible according to 1942 engineering standards. The components needed to be miniaturized beyond anything industry could manufacture. The electronics needed to survive accelerations that would liquefy human organs. The radar needed to work reliably despite massive electrical interference from the gun blast. The fuse needed to cost less than $50 to manufacture, or the military would never adopt it at scale. And all of this needed to be perfected within months, because American. Sailors were dying in the Pacific at a rate that made Parsons physically ill when he read the casualty reports. The Japanese had a weapon that was devastatingly effective. Kamikaze pilots who would deliberately crash explosive-laden aircraft into American warships. Conventional anti-aircraft guns could shoot down maybe 3% of incoming kamikazes if conditions were perfect. When conditions weren't perfect, when visibility was poor, or attackers came at dusk or through clouds, that percentage dropped to nearly 0. Ships were being lost. Hundreds of sailors were dying every week, and the problem was getting worse, not better, because the Japanese were getting more desperate and more willing to expend pilots in suicide attacks. The mathematics were brutal and simple. A 5-inch anti-aircraft shell had to explode within 20 feet of an attacking aircraft to have any chance of bringing it down. Closer was better. 15 feet was nearly ideal, but hitting a moving aircraft directly with a shell was statistically almost impossible. Fire control systems could aim accurately, but they couldn't predict evasive maneuvers or account for wind variation at altitude, or compensate for the dozen other variables that affected trajectory. Time delay fuses, which exploded at a preset altitude, were only marginally better. They required perfect intelligence about enemy altitude and approach vector, information that was rarely available in the chaos of combat. What was needed was a fuse that could detect when it was near an aircraft and explode automatically. Simple in concept, impossible in execution. Dozens of approaches had been tried. Acoustic fuses that listened for engine noise proved useless because gunfire drowned out everything else. Photoelectric fuses that detected shadows were defeated by clouds and couldn't distinguish aircraft from terrain. Magnetic fuses that sensed metal masses were too sensitive and exploded randomly. Every approach had fatal flaws. Every approach except Tuve's radar fuse, which by all conventional engineering wisdom should have been the most impossible of all. Parsons stopped the film and switched on the lights. The screening room, suddenly bright, smelled of cigarette smoke and stale coffee. On the table beside the projector sat a stack of technical reports 6 inches thick, all related to the proximity fuse program. Parsons had read every page. He'd memorized specifications, studied circuit diagrams, reviewed test results, and interviewed everyone connected to the project. He'd done this because Admiral Harold Rainsford Stark had personally ordered him to determine whether the proximity fuse program should be continued or terminated. Parsons, the Admiral had said 3 weeks earlier, his voice tight with frustration. I've got 17 review boards telling me this fuse program is a waste of time and resources. I've got one scientist telling me it's the weapon that will win the Pacific War. I've got senators demanding to know why we're spending millions on a device that doesn't work. And I've got casualty reports from the Pacific that make me want to put my fist through a wall. You're a smart man. You understand engineering. You understand the Navy. Go to Dahlgren. Watch the tests. Meet this Tuve character. Then come back and tell me definitively whether we continue this program or shut it down. I need an answer I can trust, and I need it in 3 weeks. Parsons had arrived at Dahlgren expecting to find a program in chaos, led by an eccentric researcher pursuing an impossible dream. What he'd found instead was something far more complicated and far more interesting. The program was indeed chaotic, and Tuve was indeed eccentric, but the work itself was extraordinary, more than extraordinary. It was revolutionary in ways that the review boards, focused on immediate technical challenges, had completely failed to grasp. The film he'd just watched proved the fuse worked under ideal test conditions. But Parsons knew that ideal test conditions meant almost nothing. The real questions were whether it could be manufactured reliably at scale, whether it would work in actual combat conditions, whether sailors could be trained to use it, and whether the benefits justified the enormous cost and effort being invested. These questions didn't have easy answers, and the political pressure to shut down the program was immense. Parsons gathered his notes and walked out of the screening room into the humid Virginia night. Dawn was still 2 hours away. The proving ground was quiet, just the distant sound of waves on the Potomac and the rustle of wind through trees. Somewhere on this base, probably in his laboratory, Tuve was awake and working. The man apparently never slept more than 4 hours a night. He was driven by something Parsons was only beginning to understand, a conviction that bordered on obsession that his fuse could save thousands of lives if only he could convince the military to give him enough time and resources to perfect it. Tomorrow, Parsons would meet with Tuve for the first time. He'd been deliberately avoiding the man, wanting to form his own conclusions about the technology before being influenced by its creator. But now, it was time for a conversation that would determine the future of the program and possibly affect the outcome of the entire war. Parsons needed to understand not just how the fuse worked, but why Tuve believed in it so completely. What drove him to continue despite constant opposition, and whether that conviction was based on solid engineering or on the kind of optimistic delusion that could waste critical resources during wartime. As he walked back toward his quarters, Parsons thought about that single frame of film, the explosion occurring at exactly 15 feet. That kind of precision suggested more than luck or a fortunate test. It suggested genuine understanding, mastery of principles that most engineers hadn't even begun to grasp. If Tuve had truly solved the proximity fuse problem, it would revolutionize not just anti-aircraft warfare, but potentially every aspect of ordnance design. Guided weapons, smart bombs, defensive systems that could think and react faster than any human operator. The implications were staggering, but implications meant nothing if the device couldn't be made to work reliably, manufactured cheaply, and deployed before more American sailors died in the Pacific. Parsons had 3 weeks to make a recommendation that would affect thousands of lives. He'd spent 2 of those weeks gathering data. Tomorrow, he'd start understanding the man behind the impossible fuse. He didn't sleep that night. He kept seeing that explosion, perfectly positioned, exactly 15 feet from the target. Proof that sometimes the impossible was just barely possible if someone was stubborn enough and brilliant enough to make it real. At 6 in the morning, Parsons found Merle Tuve exactly where he'd expected, in the main laboratory, surrounded by oscilloscopes, circuit boards, and at least 40 empty coffee cups. Tuve was hunched over a workbench, soldering iron in hand, making minute adjustments to what appeared to be a partially disassembled fuse. He didn't look up when Parsons entered. Either he hadn't heard the door or, more likely, he was so absorbed in his work that external distractions simply didn't register. Parsons took a moment to observe. Tuve was younger than his reputation suggested, early 30s at most, with disheveled, dark hair and wire-rimmed glasses that kept sliding down his nose. He wore the same clothes he'd probably worn yesterday, wrinkled khaki trousers and a white shirt with the sleeves rolled up, revealing forearms marked with what looked like chemical burns and electrical scorch marks. The laboratory around him was organized chaos. Equipment covered every available surface, but there was logic to the arrangement. Test equipment here, assembly tools there, stacks of technical drawings organized by some system only Tuve understood. What struck Parsons most forcefully was the absolute concentration on Tuve's face. This wasn't someone casually tinkering with electronics. This was someone operating at the absolute edge of his capabilities, making micro-adjustments to a device that contained probably 200 separate components, each of which had to function perfectly under conditions that would destroy most electronics instantly. The proximity fuse wasn't just complicated. It was perhaps the most complex piece of miniaturized electronics ever created, and Tuve was treating it like a surgeon performing a delicate operation. "Dr. Tuve," Parsons said finally. "I'm Lieutenant Commander Parsons. Admiral Stark sent me to evaluate your program." Tuve didn't respond immediately. He finished the connection he was working on, tested it with a multimeter, frowned at the reading, made another micro-adjustment, tested again, and only then looked up. His eyes behind the glasses were intelligent and wary. "Another evaluator. That makes 18 in 8 months. Are you here to shut us down, or just to waste my time with another progress report?" The hostility was immediate and palpable. Parsons had expected this. According to everyone he'd talked to, Tuve was brilliant, but notoriously difficult, dismissive of military bureaucracy, impatient with questions he considered stupid, and openly contemptuous of the review boards that kept trying to terminate his program. "I'm here to understand what you're doing and make an informed recommendation to the Admiral." Whether that recommendation is positive or negative depends on what I learn. Honest answer. Tuve set down his soldering iron and stretched, his back cracking audibly. Most evaluators arrive with their conclusions already written and just go through the motions of an investigation. All right, Commander. What do you want to know? I watched the test film from yesterday. The fuse worked perfectly. 15-foot proximity detonation, clean kill on the drone. Congratulations. Don't congratulate me yet. Tuve removed his glasses and cleaned them on his shirt. That was test number 417. Tests 412 through 416 failed. 2 premature detonations, 3 complete failures where the fuse didn't trigger at all, and 1 that exploded inside the barrel when the gun fired. We're achieving about 60% reliability under ideal test conditions. Combat conditions will be worse. Until we're at 95% reliability minimum. This fuse is a dangerous liability that will kill more of our own people than enemy aircraft. Parsons appreciated the brutal honesty. Most researchers trying to save their program would have emphasized successes and minimized failures. Tuve was doing the opposite. What's causing the failures? Depends on the failure mode. The premature detonations are usually caused by electrical transients during gun firing. Despite extensive shielding, we're still getting voltage spikes that can trigger the fuse circuit prematurely. The non-triggers are more complicated. Sometimes it's component failure due to acceleration forces. Sometimes it's the radar oscillator not starting properly. Sometimes it's environmental interference. Every failure has a different root cause, which means I'm not solving one problem. I'm solving 200 simultaneous problems, and every solution I implement creates new failure modes I have to address. Sounds impossible? It is impossible, according to 17 review boards, at least. Tuve stood and walked to a chalkboard covered in equations and circuit diagrams. Let me explain what we're attempting here, Commander, so you understand why everyone thinks I'm wasting their time. This fuse contains a radio transmitter, a radio receiver, an amplifier circuit, a mixing circuit, a frequency discriminator, a thyratron tube triggering system, and a backup battery. All of this fits inside a space approximately 4 inches long and 2 inches in diameter. The entire assembly weighs less than 2 pounds. When fired from a 5-inch gun, it experiences acceleration forces exceeding 20,000 times gravity for approximately 1/40th of a second. The shock is equivalent to dropping the fuse from a height of 6 miles onto concrete. Every component must survive this shock and function perfectly afterward. Parsons did some quick mental calculations. That acceleration would crush most metals. How are your components even staying intact? Special mounting systems. Every component is potted in a proprietary resin compound developed by National Carbon Company. The resin absorbs shock and prevents components from shearing off their mountings. But the resin had to be developed specifically for this application because standard potting compounds either didn't absorb enough shock or became brittle at temperature extremes. Developing the resin took 9 months and cost $600,000. When I requested funding for resin development, the review board asked why I was wasting money on plastics instead of focusing on electronics. Because without the right resin, the electronics wouldn't survive to function. Exactly. But explaining systems-level thinking to people who want simple answers is exhausting. Tuve picked up a completed fuse from a storage rack and handed it to Parsons. The review boards see this and think it's just a radio in a shell. They don't understand that every single component is custom designed. The vacuum tubes are miniaturized versions that don't exist anywhere else in the world. Western Electric had to build a special production line just to manufacture them. The resistors and capacitors are custom designs that can survive high G-forces. Even the wire insulation is specialized. Standard wire insulation fails under shock loading. We had to develop wire coating that remains flexible under acceleration. Do you understand what I'm telling you, Commander? You're not building a fuse. You're inventing an entire new field of ruggedized, miniaturized electronics from scratch. Yes. Tuve took back the fuse and set it carefully on the workbench. This fuse represents approximately 40,000 hours of development work across 17 separate institutions. Johns Hopkins, MIT, Columbia, Bell Labs, Western Electric, National Carbon, at least a dozen others. We've filed 67 separate patent applications for technologies developed specifically for this project. We've trained 300 technicians in assembly procedures that didn't exist a year ago. We've built testing equipment that can simulate gunfiring without actually firing shells. We've solved problems that most engineers don't even have vocabulary to describe. And despite all of this, I still can't get above 60% reliability, which means the program will be shut down, and all of this work will be wasted. The frustration in Tuve's voice was raw and genuine. This wasn't someone upset about career implications or wasted effort. This was someone who believed absolutely in the importance of his work and was desperate to make it succeed before time ran out. Parsons understood that desperation. He'd felt it himself reading casualty reports from the Pacific, knowing that every week of delay meant more dead sailors, more ships on the ocean floor, more families receiving telegrams that would destroy their worlds. "Show me your test data," Parsons said. "All of it. Successes and failures. I want to understand the failure modes in detail." For the first time, something like respect crossed Tuve's face. Most evaluators just want summary statistics. You actually want to understand the engineering? I was a gunnery officer before I was assigned to research evaluation. I understand ballistics, electrical systems, and the realities of naval combat. I'm not here to judge whether your work is elegant. I'm here to judge whether it can save lives. Show me everything. What followed was the most intensive technical briefing Parsons had ever experienced. Tuve walked him through every aspect of the proximity fuse, explaining not just how it worked, but why each design decision had been made, what alternatives had been considered and rejected, where the current limitations were, and what would be needed to overcome those limitations. He showed test data from hundreds of firings, annotated with detailed failure analysis. He demonstrated the assembly process, explaining how each component was installed and tested. He pulled out circuit diagrams and traced signal paths, showing how the radar detected targets and triggered detonation. The radar itself was ingenious in its simplicity. It transmitted a continuous radio wave at approximately 180 megahertz. When that wave reflected off an aircraft, the reflected signal had a slightly different frequency due to the Doppler effect, the same phenomenon that causes an ambulance siren to change pitch as it passes. The fuse's receiver picked up both the transmitted signal and the reflected signal, mixed them together, and generated a difference frequency. As the fuse approached the aircraft, the difference frequency increased in a predictable way. When that difference frequency reached a specific threshold, indicating the fuse was approximately 15 feet from the target, the triggering circuit fired and detonated the warhead. In principle, it was straightforward. In practice, it required solving hundreds of cascading technical problems. The radar oscillator had to be mechanically stable despite shock loading. The antenna had to be efficient despite its tiny size. The receiver had to be sensitive despite having no external power supply during the shell's flight. The amplifier had to function reliably despite temperature variations from -40 to +140 degrees Fahrenheit. The triggering circuit had to be fast enough to detonate the warhead before the shell passed the target. Every single component was operating at the edge of what 1942 technology could achieve. "Here's the fundamental problem," Tuve said, pointing at a graph that showed test results over time. "We're improving steadily. 6 months ago, reliability was at 30%. 3 months ago, we hit 50%. Now we're at 60%. The trend is positive, but military brass wants 95% reliability, and they want it immediately. They don't understand that development doesn't work that way. You can't force innovation on an arbitrary schedule. We need at least 6 more months to reach acceptable reliability. Maybe a year. But I don't have 6 months because the program is going to be shut down next month unless someone with authority intervenes. Parsons studied the graph carefully. The improvement trend was indeed clear and consistent. If it continued at the current rate, 95% reliability was achievable within 6 to 8 months. But trend lines were not guarantees. Development often hit unexpected obstacles. Problems that seemed solvable proved intractable. And 6 months was an eternity when measured in combat deaths. "What's your biggest single failure mode right now?" Parsons asked. "Oscillator stability. The radar transmitter uses a vacuum tube oscillator operating at 180 megahertz. At that frequency, even tiny variations in component values or physical dimensions affect performance. When the gun fires, despite all our shock mounting, components shift slightly. Sometimes this shift is enough to stop the oscillator from working or to shift its frequency outside acceptable range. We've tried 17 different oscillator designs. The current version is the best we've achieved, but it's still not reliable enough." "Show me the oscillator." Tuve pulled out a technical drawing that showed the oscillator circuit in detail. It was built around a miniature vacuum tube called an acorn tube because of its shape. The tube was connected to an antenna circuit that determined the oscillation frequency. Parsons studied the design, his mind working through the physics. He'd studied radio engineering as part of his technical training and understood the principles, though he'd never worked at these miniaturized scales. "Your frequency is determined by the antenna circuit," Parsons said slowly, tracing the connections on the diagram. "The antenna is part of the shell's nose. When the gun fires, the nose flexes under acceleration forces. Even microscopic flexing would change the antenna's electrical characteristics and shift your oscillator frequency." "Correct. We've tried to make the nose mechanically rigid, but there are limits. Make it too rigid, and it won't survive impact stresses if the shell hits something before the fuse triggers. Make it too flexible and the oscillator becomes unstable. We're trying to find a middle ground that doesn't exist." Parsons continued studying the diagram. There had to be a solution. The problem was well defined. The physics were understood. Someone just needed to think about it differently. "What if you decouple the antenna from the oscillator frequency? Instead of using the antenna to determine frequency directly, use a separate, mechanically isolated resonance circuit for frequency control. The antenna just radiates whatever the oscillator produces." Tuve went very still. "That would require redesigning the entire RF front end." "Would it work?" "It might. The antenna would be less efficient if it's not resonant, but we might be able to compensate with higher gain in the amplifier. The resonance circuit would need to be shock-mounted independently, but that's solvable." "Commander, are you just brainstorming, or do you actually understand the electrical engineering here?" "I spent 2 years working on radar systems before this assignment. I'm not an expert like you, but I understand the principles. Can you test this approach?" It would take at least 3 weeks to design, build, and test a prototype. But yes, it's testable. And if it works, it might solve our oscillator stability problem. For the first time since Parsons had met him, Tuve smiled. It transformed his face, making him look younger and less exhausted. "Most evaluators point out problems. You're the first one who's tried to solve one." "I'm not here to shut you down, Dr. Tuve. I'm here to figure out if your work can save lives. If it can, I'll fight to keep your program funded. If it can't, I'll recommend cancellation so resources can go somewhere more productive. But I won't make that recommendation until I understand what you're actually trying to accomplish and whether it's achievable." "Fair enough." Tuve glanced at his watch and seemed surprised to discover it was almost noon. "I've been talking for 6 hours. You must be starving. There's a cafeteria on base that serves something vaguely resembling food. We could continue this conversation there. One more question first. Why are you doing this? You could be working at any university or research lab in the country. You've got credentials from Johns Hopkins. You could have a comfortable academic career. Instead, you're here, sleeping in your laboratory, working 20-hour days, fighting with review boards who want to shut you down. Why? Tuve was quiet for a long moment. When he spoke, his voice was soft but intense. Commander, do you know how many sailors died in the Pacific last month? The casualty reports are classified, but I've seen them. Too many. Too many. That's one way to put it. Another way is to say that every 3 days, we lose enough sailors to crew an entire destroyer. Every week, we lose more than died in the entire Revolutionary War. And most of those deaths are preventable. They die because we can't shoot down enemy aircraft reliably. They die because our anti-aircraft defenses are inadequate. They die because military leadership keeps using the same tactics and weapons we used in the last war. And warfare has changed. If this fuse works, Commander, we could reduce combat deaths by half. Maybe more? I'm not doing this for career advancement or academic recognition. I'm doing this because I know how to make a weapon that will save thousands of lives. And I can't stop working on it as long as there's any chance of success. Does that answer your question? It did. Completely. Parsons had met plenty of researchers during his evaluation assignments. Most were competent professionals doing good work. A few were brilliant. But Tuve was something different. He was driven by a moral imperative that transcended normal career considerations. He believed, absolutely and without reservation, that his work mattered, that every hour of delay cost lives, that success was not just professionally important, but morally necessary. That kind of conviction could be dangerous. It could lead researchers to oversell capabilities, ignore problems, push ahead recklessly. But as Parsons thought about the 6 hours of technical briefing he'd just received, he realized Tuve wasn't doing any of those things. He was brutally honest about limitations, realistic about timelines, and methodical in his approach to solving problems. His conviction wasn't based on wishful thinking. It was based on genuine understanding of what was possible and determination to make it real. "It answers my question," Parsons said. "Let's get lunch. Then I want to see your manufacturing plans. If this fuse works, we'll need to produce hundreds of thousands of them. Maybe millions. I need to understand whether that's feasible." As they walked toward the cafeteria, Parsons felt his evaluation shifting. He'd arrived at Dahlgren expecting to write a report recommending program cancellation. The technical challenges seemed too severe, the timeline too aggressive, the costs too high. But after spending 6 hours with Tuve, he was beginning to think something different. The problems were real, but they were solvable. The timeline was aggressive but achievable. The costs were high, but justified if the fuse worked as promised. And most importantly, the man leading the program was exactly the kind of relentlessly focused genius who could actually pull off the impossible. Parsons didn't know it yet, but his conversation with Tuve that morning had changed the course of the war. In 3 weeks, he would write a report recommending full support for the proximity fuse program. That report would reach Admiral Stark, who would take it to President Roosevelt, who would authorize unlimited funding and resources. The proximity fuse would go into mass production, eventually becoming one of the most important weapons of World War II. It would shoot down thousands of aircraft, intercept hundreds of V-1 rockets targeting London, and revolutionize ground warfare when adapted for use in artillery shells. But all of that was still in the future. Right now, Parsons was just a Navy officer having lunch with a brilliant, difficult researcher who believed he could save thousands of lives if someone would just give him enough time and resources to perfect his impossible design. And Parsons was beginning to believe him. The cafeteria was depressingly utilitarian, all metal tables and institutional lighting, serving food that tasted like it had been cooked 3 days earlier and then reheated without enthusiasm. Tuve and Parsons sat at a corner table with trays of something that might have been meatloaf accompanied by vegetables that had been boiled into submission. Around them, engineers and technicians ate quickly. Their conversations focused on technical problems, test schedules, and equipment failures. Parsons pushed his food around his plate. Tell me about manufacturing. Even if we solve the reliability problems, can this fuse actually be mass-produced at the scale we'd need? Tuvey ate mechanically, clearly thinking about something else. That's a complicated question. In theory, yes. We've designed every component with mass production in mind. The vacuum tubes can be manufactured using adapted production lines from standard radio tube factories. The resistors and capacitors use conventional materials, just in miniaturized form. The circuit assembly follows logical sequences that can be taught to trained technicians. But there's always a but. The quality control requirements are extreme. Every single fuse contains about 200 components. Every component must be within tight tolerances. One bad resistor, one marginally defective capacitor, one poorly soldered connection, and the fuse fails. At 60% reliability, that means roughly 40% of fuses leaving production are defective. We can't afford that. We need to either improve reliability so fewer fuses fail, or implement testing procedures that catch defects before fuses are shipped. Preferably both. Can you test them without firing them from a gun? Partially. We've developed test equipment that can check basic electrical functions, verify the radar oscillator is working, measure receiver sensitivity. But we can't fully test the shock mounting or the behavior under acceleration forces without actually firing the fuse. We've built gas guns that can simulate firing without using expensive shells, but even those tests are costly and time-consuming. Testing every fuse before shipment isn't practical. Parsons considered this. So you need the manufacturing process to be reliable enough that testing becomes largely redundant. Exactly. Which means developing production procedures that prevent defects rather than catching them after assembly. That requires training workers to extremely high standards, implementing multiple quality checkpoints during assembly, and designing the components themselves to be tolerant of minor variations, all of which takes time we don't have. How much time do you actually need? Tuvey set down his fork and met Parsons's eyes directly. Honest answer? 2 years. 1 year to perfect the design and reach 95% reliability. Another year to scale up production, train workers, establish quality control procedures, and work out the inevitable problems that arise when you go from building 10 fuses a day in a laboratory to building 10,000 fuses a day in factories. But I know I'm not going to get 2 years. I'll be lucky to get 6 months. So the real question is what can be achieved in 6 months, and whether that's enough to make the program worth continuing. What can be achieved in 6 months? If we're lucky, and if we get adequate resources, we could have a design that's ready for limited production. Maybe 85% reliability, which isn't ideal, but is usable for critical situations. We could produce perhaps 50,000 fuses in the first production run, enough to equip the Pacific Fleet for initial combat testing. If those tests are successful, we'd have proof of concept to justify full-scale production. But that's an optimistic scenario. More likely, we'll hit unexpected problems that delay everything by months. What problems are you most worried about? Tuvey laughed, but there was no humor in it. Where do I start? The oscillator stability problem we discussed this morning is just one of dozens. The battery has a limited shelf life, which means fuses can't be stockpiled for long periods. The antenna is vulnerable to corrosion from salt water, so we need special coatings that don't affect electrical performance. The arming mechanism has to prevent accidental detonation during handling, but also be reliable enough to arm every time when fired. The safety mechanisms have to be absolutely foolproof because a premature detonation could kill the gun crew. Every one of these problems is solvable, but they all take time and careful engineering. And time is the one resource I don't have. As they talked, Parsons was forming a mental picture of the scale of what Tuvey was attempting. This wasn't just developing a new weapon. It was simultaneously inventing new manufacturing techniques, training an entire workforce, solving hundreds of cascading technical problems, And doing all of this under extreme time pressure with limited resources and constant threat of program cancellation. The fact that Tuve had gotten as far as he had was remarkable. The fact that he thought he could actually succeed seemed almost delusional. Almost. But Parsons was beginning to understand that Tuve's confidence wasn't based on optimism. It was based on systematic analysis. He'd broken the overall problem into specific sub-problems. He'd prioritized them by importance and difficulty. He'd assembled teams to work on each sub-problem. He'd developed testing procedures to validate solutions. He was approaching the proximity fuse the same way a military campaign was planned, with clear objectives, assigned responsibilities, and measurable milestones. It was methodical and professional, not the work of someone chasing an impossible dream. "All right," Parsons said. "Let's assume you get 6 months and adequate resources. Walk me through your development plan. What happens month by month?" Tuve pulled a worn notebook from his pocket and flipped through pages covered with handwritten notes and calculations. Month 1. Solve the oscillator stability problem, hopefully using the approach you suggested this morning. Simultaneously, improve the potting compound to better protect components during firing. Begin designing production-ready versions of custom components. Month 2. Integrate the improved oscillator and potting compound. Test extensively under various conditions. Begin training production workers at Western Electric and other manufacturing partners. Month 3. Address the battery shelf life issue, probably by switching to a different chemistry. Continue production preparation. Month 4. Full environmental testing, including temperature extremes, humidity, salt spray. Begin limited production of pilot-run fuses. Month 5. Live fire testing of pilot-run fuses to validate manufacturing processes. Implement corrections based on test results. Month 6. Ramp up to full production of initial 50,000-unit order. Ship fuses to Pacific Fleet for combat testing. That's an ambitious timeline. It's an insane timeline. But it's the minimum needed to have any hope of getting fuses into combat before the war ends. Commander, I need to be blunt. If this program gets shut down now, thousands of sailors are going to die who could have been saved. I know that sounds melodramatic, but it's simple math. The Japanese are sinking our ships faster than we can replace them. Every month of delay in fielding effective anti-aircraft defenses means more ships lost. I'm not exaggerating when I say this fuse could change the outcome of the Pacific War. Parsons believed him. Not because Tuve was a persuasive speaker, though he was passionate, but because the logic was sound. Anti-aircraft warfare was a critical gap in American naval capabilities. The proximity fuse directly addressed that gap. If it worked as designed, it would represent a quantum leap in combat effectiveness. The question wasn't whether the fuse was important. The question was whether Tuve could actually deliver on his promises. "I need to see your test facilities," Parsons said. "And I want to observe a complete test sequence from assembly through firing. Can you arrange that? We're scheduled to test 8 fuses tomorrow morning, starting at 0600. You're welcome to observe the entire process." They spent the rest of the afternoon touring the Dahlgren facility. Tuve showed Parsons the assembly laboratories where technicians carefully built fuses by hand, working under magnification to place tiny components and solder connections too small to see with the naked eye. He showed him the environmental test chambers where fuses were subjected to temperature extremes, vibration, and humidity. He demonstrated the electrical test equipment that verified every circuit in a completed fuse. And finally, he took Parsons to the firing range where completed fuses were loaded into shells and shot at drone aircraft. The firing range was impressive in its scale. A 5-inch naval gun was mounted on a massive concrete base aimed out over the Potomac River. Downrange, several miles away, radio-controlled drone aircraft flew predetermined patterns. High-speed cameras and radar tracking systems monitored every test shot. A small observation bunker provided protection for the test crew during firing. It was a complete simulation of naval combat conditions. designed to validate fuse performance under realistic circumstances. We fire about 20 test rounds per day, Tuve explained as they stood in the observation bunker. Each test costs approximately $1,500 when you account for the fuse, the shell, the drone aircraft if we hit it, and the labor involved. We're spending about $30,000 per day on testing. Over the past 8 months, we've spent approximately $6 million just on test firings. That's one reason the review boards keep trying to shut us down. They see the spending and the relatively low success rate and conclude we're wasting money. Are you? No. Every test generates data. Even failures are valuable because they tell us what doesn't work. We're not just randomly trying things and hoping for success. We're systematically exploring the design space, identifying failure modes, and implementing solutions. It's expensive, but it's the only way to develop something this complex. You can't just design a proximity fuse on paper and assume it will work. You have to build it, test it, learn from failures, and iterate. That process costs money, but it's money well spent if the result is a weapon that saves lives. Parsons watched as technicians prepared for the next day's tests, loading shells, calibrating cameras, checking tracking equipment. Everything was methodical and professional. This wasn't amateur hour. It was a sophisticated research operation that would have impressed researchers at the best universities in the country. Tuve had built something remarkable here, a team and facility capable of solving incredibly difficult problems under extreme time pressure. As sunset approached, they returned to Tuve's laboratory. The building was quieter now, most of the day shift having departed. A skeleton crew remained, continuing work on critical tasks that couldn't wait until morning. Tuve led Parsons to a small office he maintained, though it was clear he spent little time there. Papers and technical reports covered every surface. A cot in the corner confirmed what Parsons had heard about Tuve sleeping in his lab. "Commander, I want to show you something," Tuve said, pulling a folder from a filing cabinet. "These are casualty reports from the Pacific. I'm not supposed to have them. A friend in intelligence sends them to me unofficially. He thinks I should understand the consequences if this program fails." Parsons opened the folder and felt his stomach tighten. Page after page of casualty reports from kamikaze attacks. Ship names, death tolls, descriptions of damage. The USS Bunker Hill hit by 2 kamikazes, 393 dead. The USS Franklin, crippled by a single kamikaze that triggered massive secondary explosions, 724 dead. The USS Bismarck C, sunk by kamikazes, 318 dead. The list went on, and these were just the major incidents. Dozens more reports described smaller attacks, ships damaged, sailors killed and wounded. "This is from the past 3 months," Tuve said quietly. Over 2,000 sailors killed by kamikaze attacks that conventional anti-aircraft guns couldn't stop. Those men died because we couldn't shoot down aircraft reliably. If the proximity fuse had been available, most of those attacks could have been defeated. Most of those sailors would still be alive. That's why I'm here, Commander. That's why I can't quit no matter how many review boards tell me I'm wasting time. Because every day I delay is measured in lives. Parsons closed the folder carefully. He understood exactly what Tuve was saying because he'd felt the same moral weight reading those same casualty reports. The war wasn't an abstraction. It was real people dying in horrible ways. And if technology could prevent some of those deaths, developing that technology became a moral imperative that transcended normal considerations about cost or risk or career implications. I'm going to write my report recommending program. "Continuation," Parsons said. "I'll need another week to complete my evaluation, but I've seen enough to know this program deserves full support. Your technical approach is sound. Your team is competent. Your timeline is aggressive but achievable. Most importantly, the potential impact justifies the investment. I'll recommend that Admiral Stark authorize whatever resources you need to bring this fuse to production readiness within 6 months. The relief on Tuv's face was profound. "Thank you, Commander. You won't regret this recommendation. We'll deliver. I promise you that. 6 months from now, we'll have production fuses ready for combat deployment." "I'm holding you to that promise, Dr. Tuve, because if you fail, a lot of people are going to second-guess my recommendation." "Don't make me look stupid." "I won't. You have my word." They shook hands, and Parsons felt the calluses and burn scars on Tuve's palm, physical evidence of hands-on work. Countless hours at laboratory benches solving problems. This wasn't someone who just managed projects. This was someone who got personally involved in every aspect of development. Someone who understood his creation at a fundamental level because he'd built critical pieces himself. Parsons spent another week at Dahlgren, observing tests, reviewing documentation, and interviewing team members. Everything confirmed his initial assessment. The proximity fuse program was well managed, technically sound, and close to achieving its objectives. The failures that review boards had focused on were normal parts of development, not evidence of fundamental problems. Tuve's timeline was aggressive but realistic if adequate resources were provided. When Parsons returned to Washington and submitted his report, Admiral Stark read it carefully, asked detailed questions, and then forwarded it to higher authority with his strong endorsement. Within 2 weeks, President Roosevelt had personally reviewed the program and authorized unlimited funding. The proximity fuse was designated a top priority weapons program. Tuve was given everything he'd asked for and more. Additional personnel, priority access to manufacturing capacity, authority to requisition any components needed regardless of cost. The impossible project was now the most important weapons program in the United States. And Merle Tuve had 6 months to prove he could deliver on his promises. The 6 months that followed were the most intensive development period in the history of American weapons programs. Tuve drove his team relentlessly, working 20-hour days, solving problems as fast as they emerged, and somehow keeping dozens of parallel development efforts coordinated. Despite growing complexity, the oscillator stability problem that Parsons had identified was solved within 3 weeks using a modified version of the approach they'd discussed. By mechanically isolating the frequency-determining components from the antenna, engineers eliminated most of the vibration-induced instability that had caused so many failures. Reliability immediately jumped from 60% to 75%. It wasn't enough yet, but it was progress in the right direction. The battery problem proved more stubborn. Standard battery chemistry degraded too quickly in storage, especially in the tropical heat of the Pacific. Tuve's team experimented with dozens of formulations before finding a silver chloride chemistry that remained stable for up to 6 months. It was expensive, adding nearly $10 to the cost of each fuse, but it worked reliably, and that was all that mattered. Component miniaturization was another major challenge. The vacuum tubes needed to be smaller than anything commercially available, requiring Western Electric to develop entirely new manufacturing processes. The resistors and capacitors had to be built to tolerances an order of magnitude tighter than standard components. Every piece of the fuse pushed the boundaries of what American industry could manufacture at scale. Tuve solved this by essentially creating a new industry from scratch. He worked with companies across the country, teaching them how to build components they'd never attempted before. He sent engineers to train factory workers in new assembly techniques. He developed testing procedures that could verify component quality without destroying the parts being tested. He designed custom machinery that could produce thousands of miniaturized components per day with consistent quality. By month 4, pilot production was underway. Western Electric had converted a substantial portion of their manufacturing capacity to proximity fuse production, training thousands of workers in specialized assembly procedures. Workers, mostly women because men of working age were being drafted into military service, sat at assembly benches working under magnification to place tiny components and solder connections smaller than grains of rice. Each worker specialized in one step of the assembly process, creating an assembly line that produced completed fuses at an ever-increasing rate. The first production-run fuses were delivered to Dahlgren in early October 1942 for extensive testing. These weren't hand-built laboratory prototypes. These were fuses assembled on production lines using procedures that would be replicated in factories across the country. If they worked, it would prove the entire manufacturing system was sound. If they failed, it would indicate fundamental problems with scaling from laboratory to factory production. WWII scheduled intensive testing over a 3-week period. 100 production fuses would be fired under varying conditions, temperature extremes, humidity, different gun elevations, different target types. Every test would be instrumented and recorded. Success criteria were strict: 90% minimum reliability, with failures analyzed to determine whether they represented manufacturing